introduce Professor Fariza Tahi, who is Professor of Computer Sciences and Bioinformatics at the IPISC lab in University of Évry in France. And she has an excellent research group who primarily work on developing cutting-edge tools for RNA structure prediction and analysis, and especially currently using machine learning and AI. And we also have Clément Bernard with us, who is a PhD student in Professor Tahi's lab, who's very soon going to defend his PhD. And so we are excited to have both of you as speakers for today's seminar and hear more about your research work. So please start the presentation.
Okay, thank you very much. Thank you for the introduction. So first of all, I would like to thank the organizers. Thank you for the invitation and to give us the opportunity to present our team and our work. Just effectively, I'm the EBISC lab, and I co-head the Arobas team, which is a team which fields, research fields are algorithmics, operational research, bioinformatics, and artificial intelligence. Why in our method we use all these computational techniques. So we have a group on RNAs, RNA bioinformatics. So with my colleagues from the team, with collaboration with them, and with, of course, our PhD students, postdocs, and some interns, we try to develop algorithms, computational methods, AI-based methods, tools dedicated to RNAs from the sequence to the structure. Okay. So one of our topics of interest is about the RNA prediction and classification. As we know, RNAs can be coding, non-coding, but they can also be functional when they can play in both roles of coding and non-coding. And we have several publications. There is several publications, recent publication on this subject. The non-coding RNAs can be classified into different classes. Some are very known, like tRNAs, microRNAs. We have some classes under study, like the long non-coding RNAs, which by themselves could be classified into subclasses. And all these RNAs can have different characteristics about the sequence, structure, expression, and so on. So what we want in the group is to develop AI-based methods for the prediction of this kind of RNAs and their classification, either for classifying RNAs into coding and non-coding and be functional. It's the case of our ASOM method, for instance, or to classify non-coding RNAs is here the method MMNC shown here in the slide. So for this, our first important point was to visualize the results of the classification, to give the users the ability to see why that such RNA has been classified into one class or another, why we choose to use the technique of self-organizing maps, which indeed give we can have different types of visualization, like maps, which shown here in the slide. Another point is to the use of a reject option, which make possible to deal with classes ambiguities and also to be able eventually to detect new classes. And this, for example, has been used in ERSOM to predict the p-functional RNAs. And about MMNC, we use a multimodal deep learning, as shown here in the figure, where we use different modalities for each types of feature or characteristics: sequence, structure, expression. Okay. Oh, no. Yes. Yes. The second, our research topic is about the secondary structure prediction. We work on this field for many years now. So here I show some recent works. As we know, the secondary structure is composed of several functional motifs. We have of course, the helices, the loops, and we can have also what we call pseudonodes appearing when a loop, for instance, pair with another loop or another unpaired part of the structure. And these pseudonodes make the structure losing its planar conformation. But these pseudonodes play important functional biological roles. Why we think it's important to predict them, even generally it's difficult. As we know, too, RNAs are very unstable. They can adopt different conformation. They can switch from a structure to another. And like in proteins, RNAs can interact and form complexes. So what we try to do is to develop algorithms for predicting the different possible secondary structures. That means which algorithm able to return different solutions of structures, including the prediction of pseudonodes, either for a single RNA or for several RNAs, which will form complexes like what we saw in the right of the slide. So our approach here was to use combinatorial optimization algorithms. For instance, we developed bi-objective optimizations algorithms combined with mathematical programming to be able to predict all types of pseudonodes. Most of existing algorithms are able to predict only some types of pseudonodes, usually the simplest one, especially for the algorithm based on the dynamic programming. So here we wanted to predict the structure with all the types of pseudonodes. And this is the case of the two methods we developed, BioCop and BioRCO, where, for example, in BioRCO, we added to the objective of free energy the insertion of 3D motifs in the structure. And we have also developed multi-objective optimization algorithms combined to graphs to predicting the secondary structure, including always the pseudonodes of complexes of RNAs. And here, so we added to the free energy objective the user knowledge. So the user can enter some knowledge or constraints, and we take into account probing data like shape, for example. And this is the method CN separate, which so both methods are already published and available. Oops. Okay. The other topic I present here is the RNA 3D structure prediction. I think it's the topic which interests the most the community here. There are, of course, many methods in the literature. So in our group, we are interested by predicting the RNA, the 3D conformation of RNA from the sequence only, without taking into account knowledge of families. That means without the MSR, the multiple sequence alignment, which is usually used in the existing methods, for example, including AlphaFold. And to doing that, our approach is to use deep learning language-based method. So the first method we have developed is the RNA torsion belt, which in order to go for before how we can say it's the first step to the precision of the 3D conformation. We predict first the torsional angles and using the Dana belt in this case. And this is the thesis of Clément, who is here today with us. In the beginning of the thesis, we saw that it's problematic to have metrics, to use the metrics to evaluate the prediction, the different, the quality of the structures. So we developed a very nice tool which integrates different metrics in one and they can, these different methods can be used very easily. So Clément will present this tool just after me, and then he can explain it very well. Clément did also a very extensive and comprehensive and I think, broad state-of-the-art benchmark of the state-of-the-art, and all the results are available, and he makes available all the results on our platform, and he did also a focus on AlphaFold 3. Oops. Okay, currently we are interested by long RNAs. And as we know, contrary to the proteins, RNAs can be very long. The range, the sizes range from a few dozen to several thousand of nucleotides, and it's of RNA as the secondary structure. So our approach is to use divide and conquer approach. That means, for example, for the secondary structure, what we did is to try to partition the sequence into subsequences, smaller sequences. Then we can use an efficient tool of the small sequences, and then to integrate of the different structures which have been predicted to have the global structure. And so this is the method divide fold. Okay, and in divide fold we predict also the pseudonodes. And on the 3D structures, in this case, for this moment, we go from the 3D structure, and what we want is to have a way to partition the 3D structure, like what is done in proteins, to try to see, we're using clustering-based method to see if we can find different segments, parts of the 3D structure. And it's an 3D structures which uses, for instance, a density-based clustering method, but it's a work in progress, and we are trying over clustering methods to have better results. Oops. Yeah. So all the methods we develop, the tools we develop in the team are made available on a platform called EvryRNA. Currently, we have around 20 tools. Several of them are available as web servers, so they can be tested and tried. Almost of them also, the code, the source code is available. So yes, so you can try. Currently, I found there are some technical problems, but we intend to improve the infrastructure behind EvryRNA and to the form and so on. Okay, I have finished for my part. I hope I didn't took too much time. So I will let Clément present the RNAdvisor tool, which are here in the platform, RNAdvisor 2, and so we have to.
Hello, can you hear me? Can you all see my screen?
I think I have.
Okay.
I did it. I stopped or not yet? No, it's okay. I think it's okay.
Yeah, it's okay.
Yes, I don't need to stop. Okay.
Okay, so thank you for the invitation. Yes, so I'm Clément Bernard, a PhD student, and I'm going to talk about how to assess structural quality in a unifying way using RNAdvisor and its second version. So first of all, in terms of quality assessment, so we have given a predicted structure and a native structure. For instance, let's say we have aligned structures. How can we assess the RNA structural quality, and with or without reference? So that was a question, and this is also what is done in CASP, just to assess all the benchmarks. And so, for instance, given let's say we have 3 models of predicted structures. And so the metrics are a way to assess their closeness compared to a native structure, which she will often try to compare to a native structure. So let's say we'll do some alignment and then compute, I don't know, root-mean square deviation or other metrics. And so this is the metrics. So they are used to assess the quality of model in terms of benchmarking, for instance, and they are based on dissimilarity with a comparison of a native structure. And so there are different type of metrics. So you have the general metrics, for instance, root-mean square deviation, or just a clash score, for instance, that will count the number of atomic clashes. You also have some protein-based methods that are like taken from the protein world, I would say, like the TM score, GDTS, LDT, etc. And then you also have more RNA-oriented metrics, which will, for instance, take into account the key RNA interaction, the torsional angles, which are specific to the RNA. And so, for instance, the mean of circular quantities, so the MCQ, so it will take predictive structures. It will extract the torsional angles for each nucleotide. You will get a few torsional angles, seven or eight torsional angles. And you will do the same with the native structures. And then you will try to combine them to have a metric that will assess how close we are to the native structure in terms of torsional deviation. So in terms of angle deviation. So this is an instance of a metric. But in fact, we to have a metric and to assess the quality of a prediction, we need to have a native structure reference, which in fact is a strong requirement. And so when we develop deep learning models or even ab initio or template-based approaches, we may not have access to that native structure. And so there is an interest of having being able to predict the quality of a structure without any reference. And so this is what we call a scoring function. So let's say we have three models. And so the interest of scoring function is to try to rank them. So let's say here the purple one looks a little bit worse than the other ones. And then we'll get like the top structure, the top ranking of the structures based on a value which will be the scoring function. And so the idea is to give a score, a nativity-like score, to allow the ranking of the structure without any reference. And so there are two different types of scoring functions. So you have the knowledge base, which are which considers some statistical potential, for instance, and you have some new ones which are like a deep learning scoring function, like RS, for instance. And so this is like the scoring function we've been developing. So previously I introduced the MCQ. So the idea was given a structure, try to get the torsional angles and then get the same torsional angles from the native structure and do the comparison in the torsional space. And so here it's kind of the CMID. So given the predictive structure, we do not have access to a native structure. So we'll just extract the angles from that structure. And we'll try also to predict the torsional angles, which with a model that we developed, which is RNA torsion BERT. So we'll extract the sequence and then feed it into the deep learning network, which will predict the torsional angle. And so these torsional angles will be considered as a native one. And then we can just compute the MCQ like. And so it's just a replacement of the true structure angles with the prediction of the model. And so in that way, we do not have a metric, but a scoring function because we are reference-free. We do not have that native structure. And so we try to reproduce the MCQ. And so instead of the root miscalculation, for instance, for RS, or even with the low-key parse scoring function, which tries to predict the LDDT. So here we try to predict the MCQ. So it's for another use case. But anyway, we don't have, in fact, a universal metric or universal scoring function to say, okay, this is the correct way to assess RNA quality. And so each metric, each scoring function has its own specificity, and they might be also complementary. And we do not have access of everything in a single platform. Like each tool is developed by its own research group. And so it's not also scalable for automation. And so that's why we try to develop a tool just to make the automation of evaluation of RNA-3 structure easier. And so this is what we call RNAdvisor, and also RNAdvisor, the second version. And so the idea of RNAdvisor is to really gather all available metrics and scoring function in a unique interface, usable easily in command line with all the installation already done and available. So it uses Docker and Docker files. And so it enables the automation of structure evaluation. And so, for instance, given RNAdvisor, you feed a predictive structure, and so it will output scoring function. So the first version we had a 4 scoring function, And also given one predicted structure or predict structures and a native structure, then you can compute different metrics. So at the beginning, for the first version of RNAdvisor, we had around eight metrics. And then with the second version of RNAdvisor, we switched from 4 scoring function to 12 scoring functions. So all available with the command line. And also given the native structure, you can get also the different metrics. So kind of the same that we had previously. And also what is also a change in the second version of RNAdvisor. So in the first version, we had like one Docker file for all the scoring function and metrics. And like for the second one, we have a container for each specific scoring function, each specific metric. And so it allows you to like choose one specific scoring function if you want to use it, or one specific metric, or just run it separately. And it allows easily to add some new metrics, new scoring function quite easily. Just need to add some Docker file and then it will be added. And so in terms of containers, so as I said, each one has its own Docker file. It's also available with pip install with RNAdvisor. And we also try to reduce the size of each container. So for instance, when we try to get PAMnet a scoring function into Docker file, like the original Docker file was around 15 gigabytes. And so we try to reduce everything that was useless. And so we ended up with 3 gigabytes for Docker file. And then we use also Docker Slim, which allows really the reduction of Docker images. And so at the end, we have an image of less than 1 gigabyte. Same for arrays, for instance. And so also the containers are orchestrated with Docker Compose. So like you can run different metrics and like each Docker will be run and everything orchestrated with Docker Compose. And also, so given the fact that we have access to all metrics and all scoring function, as there is no unique metrics, so we thought about the meta metrics that were introduced in CASP 15 and also in CASP 16. So it's kind of like a weighted sum of available metrics. And so we wanted to do the same with what we had. So in fact, we used like just a weighted sum of all the existing metrics that we had. And we also wanted to introduce another kind of meta metrics. So in fact of having the z-score for each metric, we wanted also to have a normalized score with a min-max normalization. So that let's say we have like 11 metrics and we do the n sum. So the interest is to have a score between 0 and 11. And we know that if a given metric has a like normalized sum of 11, we know that it's the best. Whereas if it's near 0, we know that this is kind of the worst amongst the pool of structures that we have. And we also wanted to try to do the same with the scoring function. So as there is no universal value and we had access to a lot of scoring function, why not try to have a meta scoring function? And so we just try to do a proof of concept with a z meta, which is a sum of 4 scoring function. So 3 of them were chosen because they was kind of the best on the benchmark that I will show just after. And another one, the TBMCQ, it was because it was the best based on the MCQ, so the torsional based, which was less the case for the other scoring function. So that's why we wanted to have just a proof of concept of this meta scoring function. Of course, if we wanted to increase the quality of that meta scoring function, we could add some weights around each of different scoring function and try to optimize those weights. Here it was just a proof of concept. And also in the second version, we try to have a web server, which is available in the EvryRNA RNA platform. And I will do I will show it just after. I will do a demo on that. And then, so once we have the metrics and scoring function, so can we do a benchmark about like how do metrics correlate to each other? And so this is what we'll do. So we use the Pearson correlation coefficient. And also in terms of scoring function benchmark. So the idea of scoring function is kind of reproduce the metric, but without the native structure. And so how is the correlation with a given scoring function with existing metrics? And also when we add a native structure, how does it rank in the overall rankings that we have? So this is a question that we'll try to ask. And so here, this is the PCC that we compute. So for instance, given a scoring function and a metric, we compute just a kind of correlation between the scoring function and that metric. It will give us like a score between 0 and 1. And whenever this is 1, it means it has kind of a high correlation between that specific scoring function and that metric. And so in terms of dataset, we use 4 datasets. The first one with 85 RNA and 500 decoys. The second one from decoys, like with 20 RNA and 40 decoys. And the third one was from RNA puzzles, and the fourth one was from CASP RNA 15. And so here we can see, like for the given matrix, we have the PCC. So it's a score between 0 and 1. And so the lighter, the higher, the better. And so between each of the metric, within the metric. So the idea was to see how like complementary or how linked are the metrics between themselves. And so for instance, so the DI is deformation index, which is computed between the root mean square deviation and the INF. And so it has a high correlation with root mean square deviation and INF. So, okay, it makes sense. Then we can see, for instance, the root mean square deviation, which correlates with a coarse-grained LDDT. We also have CLDDT, which has a high correlation with epsilon RMSD and TM score, for instance. Also, the epsilon RMSD, it's kind of highly correlated with INF, which kind of makes sense because epsilon RMSD tries to add some key RNA interaction in the root mean square deviation. So this is what we have with the INF. We also have high correlation between GDTTS and TM score. We also have for the p-value, which is like p-value associated with the RMSD, which has like kind of a low correlation with the other metrics. And this is also because the p-value give you a, just like if it's close to 0, it means that we do not have a random prediction, whereas if it's really high, it might means that we have a random prediction. So this is like either very close to 0 or either 1. So makes sense that it's not really high as correlated as the other metrics. And same case for the clash score. So it is kind of uncorrelated to the other metric because it's kind of just the quality of that structure without any link to the another prediction, I would say. And so but it still has a correlation around 0.6 to the LDDT, which is an interesting result. And we also have kind of the LCSTA and MCQ, which are some angle-based metric, which are kind of less related to distance-based metric. And so here, this is for the scoring function evaluation. So here I show like for all the scoring functions and for all the metric, the different metrics, the correlation which are averaged over the 4 datasets. And so it's the same in the PCC, so between 0 and 1. And so if we are close to 0, it means there is no correlation. Whereas if it's close to 1, there is like kind of high correlation between that metric and that scoring function. And in fact, we do the ranking based on the sum. So this is like a kind of the sum of all the metrics that we had. And this is kind of like what we want to optimize in this benchmark. And so we sorted the scoring function on that base. And so the best one is like compared to the other one is a meta scoring function with a correlation of 0.74. But not for all the metrics. So for instance, the best metric for the best scoring function correlated to clash score, for instance, is RNA break. And we also have like high correlation with TB MCQ because it tries to reproduce the MCQ with that MCQ metric. And also, so given, let's say we have scoring functions, so the aim of scoring function is to rank the different structures. And so given that scoring function, we'll have a ranking. And so here the worst one seems to be the purple structure. But what if we add the native structure in that pool? So let's say we add all the decoys, but the native structure. And so one way to evaluate the different scoring function is to see is the native structure on the first ranked structure among that ranking. And so this is what we did in this table. So it counts for each scoring function the number of times the native structure is found as the best scoring function. And so, for instance, with the RNAsp, like for tested 2, we have 16 times out of 20, the native structure is found as the best structure based on that ranking. And so in total, in the 4 dataset, we have like 111 out of 138 native structure, which is found as the best one in terms of that specific scoring function. And for instance, like the previous best scoring function in terms of correlation with our meta metric is ranked as the 4th in terms of ranking the native structure. And so we see that for different scoring functions, we'll have different behavior. So if you want to rank the native structure, you will not use the same scoring function, I would say. And also, there is a computation time for each scoring function and each metric. And so here we can see, depending on the RNA length, we can see the average time computed for that specific length of RNA for the different metrics, Yes. And so we can see that the most expensive one in terms of computation is the LCSTA, which is an angle-based metric. And also, so here we have for the different scoring functions. So same, given the RNA length, the average time of computation. And so, for instance, for ARES, the computation is done on CPU. And so for like a structure of with a length of higher than 2,000 structures, 2,000 nucleotides, we have like a 13-minute time prediction for ARES, which might be a bottleneck, in fact. We also have high computation for RASP or RNAsp, which we need to keep in mind that this might be a bottleneck for future development of different deep learning models or whatever models around RNA structure prediction. And so in terms of summary, so we have correlated metrics and also uncorrelated ones. So for instance, the angle-based versus the distance-based, the clash score. There is also a huge interest of using the metametrics, which has been used in CASP 15 and 16. And also for the different scoring functions. So using meta scoring function might be a way to improve correlation with metametric, for instance, but not always be the best for ranking native structure. And we should also consider computation time. And so here is an example of the RNAdvisor web server. So given that web server, you can choose from selected examples. You can also upload your own native structure and predicted structures. And so here you get the matrix or scoring function scenario. So you can choose among the different metrics that you want to compute. Then you can like select some optional parameters. So here we add the meta z-sum and min-max normalization. You can change the threshold. And so here, for instance, we have the obtained data frame. So given all the prediction that we have, you get the LDDT, all the different metrics that you input. You also have the normalization with the z-score or the min-max, for instance. And here you have a bar plot. So here we see the interest of not having the z meta score, but the normalized with the min-max, so that we can see at the end which one is the best, but also on which metric. And so here we have like the normalized sum of metrics, and so the higher the better. And we also have details for the specific metrics that for the score of different specific metric. Here we have the polar plot around the INF metrics, so Watson Crick, non-Watson Crick. And we also have like the time plot for each specific metric. And we can do the same for the scoring function. So you can upload an example or just upload your own. Then select the scoring function, so it will remove the native structure. Then select the different scoring function you want to compute. Run the task, and then you will get kind of the similar result. So given the models, you will get the different scoring function. There is also the normalization. So here you still have a plot of normalized scoring function. So it might also be interesting for some benchmark, for instance. We also added for the, so this is for the TBMCQ. So for the TBMCQ, you will get a MCQ per residue. And so you get that information as well if you select the TBMCQ. You also have information about the so the predicted MCQ for each torsional angle if you need it. And still you also have some time plot for the specific scoring function. And so we can see RS takes quite a long time. And so as a conclusion for RNAdvisor, so I think it might be a helpful tool to automate structural assessment and to also include in different benchmark to add to get some specific scoring function and even develop other scoring functions. It also enables the extensive benchmark and mostly the creation of metametrics and meta scoring function as you have everything available. And so it's freely available in the EvryRNA platform. And there is also an extension to web server, so you might like play a little with some small molecule. And so as we discussed previously, it's available in the EvryRNA platform. So thank you for your attention. I don't know if you have any question.